start recording. And we can work a little bit on that. Section 6.3. Okay. So the idea is that in a regular change of variable, you do something like f of x equal u, for example, x squared over 2 equals u. And that's a direct substitution. But at some point, you can do things like, I don't know, x equals u squared over 2, or maybe x equal a sine theta. We have already done this stuff many times, so it will be familiar. However, we are going to see that there are some substitutions that are not immediate, but will be very useful in it. Concretely, I'm going to write down here the trigonometric substitution to replace all trigonometric substitutions. I can guarantee you two things, guys. One is it always works, and two, it's generally much more complicated than any other. That substitution is that thing right there. In any case, let's let that sleep and do some math to flex our mathematical muscles. We have that thing right there. And our substitution, there is a square, there is something, there's a square root, there is something square. This screams, do trigonometrics with me. Okay, if you ask for it. So we could pick up sine, cosine, we could even pick tangent of the half angle. My recommendation here is that you go for the sine and say 2x is sine of theta. Why 2x? Because this 4 is 2 squared. So now if we go we have this, so the 2 will go dividing, and what you will have is 1/2 cosine theta, differential of theta, the square root of 1 minus sine squared this is cosine squared. Boom, boom. Good morning. Sometimes math is beautiful with us. So this is the integral. Now we have to revert the change of variable. This thing right there. And there we go. Trigonometrics make our life better, objectively, I mean. Problems you may find here in this step. The solution generally works in both directions, so please make sure to do that properly. And otherwise, if you have an integral like this, actually, let me show you. If you have an integral like this, but in your square root, you have a squared minus x squared. So any positive number here, your change is x over a equals sine theta. And let's see what happens here. That right there. Sorry, this is sine. This a squared comes out of the square root as a, so it cancels here. And what we have is the integral of differential of theta, because this is 1 minus sine squared, so it's cosine squared. The square root of cosine squared is cosine, divided by cosine is 1. Sorry. So this is wait, give me a second. That right there. However, if you find yourself in this other way, if the coefficient is multiplying the x, and this is basically the integral that we had done previously. And you get something like that. Now this is making me wonder. This is making me wonder. I think I'm missing an a here. So this is kind of to illustrate where to go in each of these integrals. If the coefficient that is not 1 is without the x, it divides. If it's with the x, it multiplies, and the idea is that you can cancel the square root. Now, So what can we do here? That's a plus, so it may complicate things. This is 3 squared. So this suggests some trigonometric substitution may work. Which substitution may work? Well, since we don't know, and sine or cosine don't seem that they will work, we're going to try that thing there. From here, let's remember the things with this substitution. I think it was like that. Sine, cosine. Good. So let's see what happens here. If we do this, we have x cubed different. Give me a second. This is in there, and now for differential of x is 1 plus tangent of theta halves square differential of theta, right? Three tangent of u equal x. It may work. It definitely may work as well. We'll do like that afterwards. It may be simpler, actually. And this has helped us in absolutely nothing, because there's something there. Definitely these three plays a role. So let's see what we do there. If we do x equal 3 tangent of u, just so dx is this thing right here. Oh, good eye, Nikki, really good eye. That thing right there. And here we have the square root of, this is 3, this squared is 9 sine squared over cosine squared. Sorry. This thing right here. And when we do this, this is 3 in power 4, so I'm going to take it out of the equation. And in the numerator, we have sine cube divided by cosine in power 5. And in the denominator, we have 3 square root cosine square plus sine square divided by cosine square. This is what? This is 1. So now they have is cosine square that is dividing, cosine fifth that is dividing. So this whole root will cancel with the fifth cosine here. So now we can write this integral as that thing cancels over there. Sine cube divided by cosine in power 4. And let's face it, it doesn't look too good, right? Let's see what we can do here. This is sine squared times sine. So we can write it as sine 1 minus cosine squared. So if we separate this, we have sine theta divided by cosine fourth minus sine theta cosine squared over cosine fourth. So this cancels here. Okay, it's still in the image. So now we have some very nice trigonometric equations that we may be able to tackle by using the change cosine theta equal t. In this case, minus sine theta differential of theta is differential of t. And our equations become minus differential of t over t fourth minus differential of t over t squared. This definitely is easier to work with. Now this minus with this minus, we can cross that out. And these two integrals are immediate. The first one is minus 3 in power cube, t in power minus 5 divided, minus 3, divided by minus 3. And this other one is t in power minus 2. So t in power minus 1 divided by minus 1. Fair enough. These 3 cancels here. I'm going to write it already in the good order. And we have 9t minus 3 minus 27t minus 1. That already has good form. So now we're going to undo the substitutions. In order to do that, I'm going to take a super ugly looking arrow up here and do it. Now, we know t is cosine of theta. So our function is 9 over cosine cube of theta minus 27 over cosine of theta. Now, our substitution was x is 3 tangent of theta. If you find yourself that using the variable u, it looks better and makes it easier for you to do these problems that using theta or using whatever other letter, as long as you use the same all the time, it will be all right. And if I remember correctly, all right. So this or something similar to that. Okay, somebody please come here and prove me wrong, because these fractionary exponents don't look good. That looks pretty bad, honestly. You know that feeling when there is an incredibly slight small detail that keeps sliding off? Well, that's exactly this moment. So that makes a little bit more sense. So this is 9, this thing in power minus 3 is the inverse fraction in power 3. So 9 plus x squared cube and 27 square root 9 plus x squared divided by 3. We add an iteration constant and we are good to go. Now that doesn't look half bad. I'm gonna check if you can, yeah, you can see it. So the problematic with trigonometric substitutions is the moment in which you have to go from tangent to cosine and one number slips. In that moment, you really have trouble. So if there is one thing I would recommend you to memorize regarding integrals is the details of the change tangent of theta equal x and tangent of theta halves equal x. Because otherwise it's kind of complicated. It gets a little bit messy, as you can see. There is generally many correct forms to an integral such like this, but there is always one that is extremely simple. In our case, this looks like a polynomial, which is pretty good, arguably. And also a sign that we may have done something wrong. But let's take 10 minutes break and we will check that afterwards. Thank you for the reminder. It happens sometimes, like, I don't know, one every 2 days. We can call it a tradition. Now, I will go through it again. The idea of improper integrals is the limit of an integral. So in order to solve it, we have to solve both. The idea is that our function will not be bound at one of the limits. So we treat it as the limit of something that is bound. We solve it, and then in the last step, we take the limits. The perfect example here is 1 over x. This is not bound in 0. It just goes up and up and up. This is a vertical asymptote. So in order to solve this integral, we should treat it in this way. Let's see what happens. By the way, I have never solved this integral. This is the logarithm of x this is pretty bad, right? This is pretty bad. However, let's see if we can rephrase that. Well, I search for this. You're going to say, hey, but isn't this integral actually infinite? And well, yeah, it actually is. I'm saving here. The trick is this function does not rise fast enough, so this area can be limited. So this it's actually infinite. Can this happen? Yeah, absolutely. So absolutely that I actually show you this example. Okay, so we already know how to attack improper integrals. Now let's do it. Let's see what the book recommends we do here. Okay. Now, first of all, in which point is this function not bound? In the infinite. So we take that limit. Right? Okay. This integral is immediate. This x minus 1 in power minus 2 divided by minus 2. If we evaluate this, we have the limit, n tends to infinity of minus 2 minus 1, 1. And this is 1/2 minus 1 over 2n minus 1 squared. Right? Now, limit when n tends to infinity of this quotient here. Zero. When n tends to infinity, this denominator becomes infinitely large. So this full thing cancels to 0. And so this limit is no other than 1/2. And that's the value of the integral. Now, I'm going to show you another example on how we manipulate these things. A 2/3. Yeah, 2/3. Now, here we don't have infinite in the limits of integration. However, when in x equals minus 1, the function is not defined. This function has a vertical asymptote in minus 1. So this is the limit we have to take. This is the limit of integration we have to take the limit to. So this is the limit when n tends to minus 1. Of our function. It tends to minus 1 from the right because it's the lower limit. Otherwise, it would tend from the left. Now, this integral is immediate. It's x plus 1 in power 1/3 divided by 1/3. So the upper limit is 2 in power 1/3 divided by 1/3, so multiply by 3, minus divided by 1/3, so multiply by 3. So this is equal to the limit when n tends to minus 1 on the right of 3 cube root of 2 minus 3 cube root of n plus 1. Now, when x tends to minus 1 on the right, what happens here? We have the cube root of a positive amount, so it's positive. And what happens here? All this argument tends to 0. So it cancels out. And this is what we have. Lower bound 0, upper bound 2. Okay, yeah. If you remember when we were talking about substitutions, one thing we mentioned once, because we have never used it again, is that the limits of integration also change. So if you do this, the limits of integration shift, actually. There might be a chance, though, that they use limit 0 and 2. Let me check here. Interesting. Now, if they change the limit of integration, that there must be something else going on. Anyway, if you have been paying attention, you'll figure out that the idea is pretty straightforward. You have one of the values, you have to take the limit on, the other value is generally respected. And well, here in both cases, the value on the amount limit has gone to 0, which is helpful. But this may not always be the case. So this equation here begs for a substitution. So let's do it. Our substitution will be sine of x equals u. So you have that thing over there. If x equals 0, u equals 0. If x is pi halves, u is 1. So we rephrase the limit of integration, and I have the integral from 0 to 1 of differential of u, 1 minus u 2/3. So now which problem do we find? In the upper bound, 0 denominator. So you have to do the exact same thing. We take the limit when the upper bound goes to 1 on the left, integral from 0 to n. All right. So we have that. That integral should be immediate. but I'm going to do a small transformation here. Yet another one, I mean, or maybe not, or maybe yes. What do you say, guys? Do I do another transformation, or we try to solve this in once? Let's go. So now we do 1 minus u equals w. So differential of u is minus dw, and the limits flip around. Right? What's the magic here? The magic here is that this minus allows us to flip the limits around. So this thing is still working. So let's see what happens here. This is the limit when n tends to 1 minus of w in power 1/3 over 1/3 between 0 and n. That thing right there, because the term in 0 is 0. Now you may be wondering, do I have to undo the substitutions? No, you don't. The reason why is because each time we do a substitution in a definite integral, we are moving the limits of integration accordingly. And finally, we are moving the limits back and forth to make them more easy to manipulate for us. In our case, when we did the first substitution, we have to do it because it comes with the substitution. Then we take the limit. When we take this variable, if u equals 0, w equals 1, and if u equals 1, w equals 0. So the limits flip around. What I'm doing is looking at the function from the other side. Finally, since this change comes with a minus sign, what I do is use this minus sign, fundamental property of definite integrals. If you put a minus sign there, the limits flip. So I flip them again to make it easier to manipulate. I do one extra step, but it's way easier to follow. So in the end, what we have is the limit of this thing here, which is, and what is the cube root of 1? Exactly, 1. So we're finished. Yeah, it can be a little confusing the first 500 times you do it, but you have to be very, very strict with how you manipulate the limits of integration, because that's by far the most important part of the problem. In this case, what you should be aware of is that 1, that becomes n. But anyway. Oh, with two limits. Okay. So we can agree that this function goes to 0 in both extremes, right? In minus infinity, it goes to 0. In infinity, it goes to 0. So the function probably does something like this. I don't know. I'm actually not going to check in detail. But the idea here, we have two limits of unboundedness or undefinedness. So what we are going to do here is treat both at the same time. Like so. And let's see what happens. From here, we have that integral is immediate. The numerator is the derivative of the denominator. So first, ridiculously obvious thing that we notice. It happens sometimes. These two things are the same. So the integral is 0. This probably does something like that. This function. Maybe. Yeah, definitely. Because this x changes sign on 0, but this is positive. So yeah, it's definitely something like that. One may be interesting in evaluating the critical points, but that person is not me. So yeah, if you find that the value of an improper integral is 0, that's perfectly fine as well. It sometimes surprises you. Now, let's do one more before my pen dies and I need another one. And we are asked to evaluate the integral Okay, sine function, it's defined as x over the actual value of x. And this is plus 1 if x greater than 0, minus 1 if x smaller than 0, and 0 if x equals 0. So yeah, 0 has no sign. So we notice that if x is greater than 1, this thing is greater than 0, so the sign is positive. And if x is between 1 and 0, the sign is negative. So we actually have to split this integral into two. Here the minus comes from the sign, because it's negative between 0 and 1. Now, what happens here? That right there. That thing right there is minus 1/3. And now evaluating the second one, plus 8/3 and minus 1/3. So 2. Aha, you were expecting an improper integral. Got you there. Alrighty. So I'm going to show you a tricky one indeed. Number 39. Number 39 asks us to evaluate this integral here. That thing right there. Now, what do we notice? The sign of x in 0 is 0, so this function is not bounded there. So we have to split it into two. This is obviously two limits, but let's try and find the value of this integral first. Have we solved this integral already? Yeah, we are splitting it because in x equals 0, this function is 1 over 0, so it's infinite. It's not well bounded there, so we cannot calculate that part of the integral. Okay, so in order to solve, first of all, we're going to solve the indefinite integral here. This is minus cosine. And here, what shall we do? We may do a substitution, probably something like that. And here we start substituting. Sorry. Which helps us in absolutely nothing. Or does it? Or does it? This is probably not the way we want to focus it, right? Oh. Don't know about you guys, but I'm just not seeing it. Or maybe I do. This is the moment where we are going to take our magic trick and see how it works. Now we substitute. there on the sine and the differential of u. So let's see what happens there. Now, first of all, one cancels here, another cancels here. Right? This shouldn't be this tricky. There must be something I'm missing. Okay. So we have very little time left. So I'm going to kind of spoil you this integral. If you check it in mathematical software like Wolfram Alpha or whatever, you will find it in this form. But this is what it means. Oof. Okay, now I see how we are supposed to solve it, but it's still a little bit tricky. So I will go over this one in the workshop on Friday probably. So if we believe that, first of all, our I minus that we are going to call is the limit when the greater bound tends to 0. Evaluated between minus pi halves and n. Now, this is minus the logarithm of 1 plus sine n over cosine n minus with this minus becomes a plus, logarithm of 1 plus sine minus pi halves cosine minus pi halves. This thing is 0. Because the cosine of minus pi halves, no, this actually not 0. We expected it to be, but it's not. The cosine of minus pi halves is 0. It's exactly 0. So here we have something indeterminate. Let's see what happens with the other integral that we will call I plus. Sorry, n tends to 0. 0 minus 0 plus. This is minus the logarithm of 1 plus sine pi halves over cosine pi halves minus with this minus plus so this is how we are going to look at it. Look at this thing. This whole thing, sorry, I'm going to start deleting things here. Let's see, the terms that we depend on. Logarithm 1 plus sine small n cosine small n minus logarithm 1 plus sine capital N cosine capital N. And here, the difference of two logarithms is the logarithm of the quotient. So I'm going to do that directly. And now we can use the same trick, difference of logarithms, the logarithm of the quotient, to figure out another logarithm here. Now, this expression is indeterminate. Happens sometimes. So what shall we do now? First of all, I'm going to write the limit here. Limit when n tends to 0 minus and n tends to 0 plus. So if both of these things tend to 0, what happens here? This is 1. This is 1. 1 plus the sign of 0 is 0. This is 1 as well. And this thing is 1 plus 0, 1. So all this thing here is the logarithm of 1, which is good. Okay, so we only have to take care of this. The only problem is we have 0 multiplying and 0 dividing. How do we do it? I'm going to rephrase it as a limit, because it's the only tool we have to deal with things like that. I'm going to call the limit theta and say theta tends to pi halves minus. We have the limit 1 plus sine of pi halves. Okay. First of all, the sine of pi halves is 1. The sine of minus pi halves is minus 1. So we have a problem there. We have 0 and 0. This might be an issue. This is our limit. Now, how do we solve this? First of all, when theta tends to pi halves minus, we are in these two quadrants here. This is theta, this is minus theta, and this is the cosine. So they have the same cosine. In the limit, we can cancel these two. Now, can we evaluate this limit? When theta tends to pi halves minus, the numerator is 2. The denominator is unfortunately 0. So this limit is infinite. Conclusion? The function diverges. I mean, the integral diverges. Now, I'm sorry I've eaten through a couple extra minutes. I'll try not to do it again. So, final round of questions before we call this a day. It's bedtime. Oh, I wish it was bedtime. All right. So thank you very much, guys, for joining. It has been fun. I'm going to check if someone has come up late, and we can call this a day. Indeed. That's here. Okay. Okay, so this was it. Thank you very much for joining, guys. I will see you on Thursday, 10:15 a.m. with whichever topic you have next. Have fun.